What is up, everybody? Welcome back to another video from the Mathnasium. I'm your host, Mr. Slagley. And today, we are going to kick things off. Here I am. I'm in Kenai, in my second cousin twice removed's garage. Well, the reason I'm in the garage recording this video is some kids had to go to sleep or something. I don't know. Why? I don't know why they had to go to sleep. Definitely no justification for that. I was gonna film it in the camper, but my third cousin twice removed already beat me to it. So he's filming a stats video in there right now. So let's get started. Let's recall a couple things from yesterday in day 1, 2-2 density curves and normal distributions. A couple key things we learned, and actually the z-score was before that, but the empirical rule only applies to a distribution that is normal. And we have this, if you have a normal distribution, we know that it's centered on our population mean and our population median because it's symmetric. And we know that if we calculate this thing called the standard deviation, which is like roughly if you were to randomly select, it's the typical value in the set's distance from the mean, okay? And if we were to calculate the standard deviation for the data set, we get some number, and if we add that number to the mean, we can make the, once, twice, 3 times, we can make these steps to the right, or subtract once, twice, 3 times, we make these steps to the left. Now, with a normal distribution, we know that 68% is held within the first standard deviation, 95% within 2 standard deviations, and 99.7 within 3. So this is called the empirical rule. We're going to be using that again today. And also this idea of a z-score. Z-score is basically, there's also a rabbit in the garage, so I apologize for the background noise. A z-score is basically just, if you have a data set and you look at an observation, every single observation in the data set is going to have this standardized z-score that tells you how rare that observation is. And the example we used was Zeisel had that super long wingspan, right? And so his fell 2 standard deviations above. The larger the z-score in the positive or negative direction, it's telling you how many standard deviations away that particular measurement was from the mean. It's very valuable. It tells you how rare it is. The larger the z-score, the rarer it is, or rather the more extreme the z-score could be negative, the rarer an observation it is. But most of them, the z-score is going to be fairly close to 0. That's a standardized distribution, standard normal. Anyways, let's move on here. So when we are saying that something is a normal distribution, there's a couple ways that we'll write it. So let's take a look. You're going to see this notation where it has a capital N, and then I'm going to get parentheses, and there's 2 slots. This is not a point like in algebra. When you see N parentheses and then these 2 numbers, what it means is we have a density curve or a distribution that has mean in the first slot and standard deviation, sigma, so mean mu and standard deviation. So it's basically just a quick way to set up a problem. So we can talk about the inputs for the problem. So for example, if I said what proportion of 2020 SAT scores were less than 1,000, we want to answer this question. This is a question from last time. We would say, well, we're going to use a normal distribution with mean, with mean 11, stop doing that, 50, there we go. I wasn't talking to a student there, I was talking to the computer. With mean 1150 and standard deviation 150. And we determined these values last time. So mean 1150 for SAT scores, standard deviation 150. And to answer this question, we can say, oh, sweet, let's go to here. Here's my mean, 1150. And if I go 1,000, right, that's lower than my that is lower than my mean by exactly 1 standard deviation. So I can say, what proportion of SAT scores were less than 1,000? Well, this is easy for me to answer because that falls right on a standard deviation measurement. Okay, it falls right in this area. So that's right on that subtracting 1 standard deviation. So I can go back to the empirical rule and I can say, all I have to do to determine how rare that observation is I have to add these up. So 0.15 plus 2.35 plus 13.5, which is a total of 16. So your answer there is going to be 16% of the students that took the 2020 SAT, about 16% scored lower than 1,000 on the test. So we can make these quick calculations. That's great. Fantastico. Another way that you can write this, you can also write it so it looks like P parentheses X less than 1,000. And what this really is saying is what is the probability, okay? So we would say this asks the question, what is the probability that a randomly selected test taker in 2020 scored less than 1,000 on the SAT? So this is a probability question because that's really what it is. What is the likelihood that a randomly selected test taker scored less than 1,000 there? Make sure I'm tilted down here, good. So these two things are asking the same question. What proportion? Same thing as asking what's the likelihood or what's the probability, that's what the P stands for, that X is, or rather that a randomly selected person that took the test scored less than 1,000. Kind of repeating myself here. And I will write that down really fast. Feel free to fast forward, but let's just do that. Hopefully this isn't. What is the probability? Oops. What is the probability? I'm going to abbreviate that. That a randomly selected test taker. Oh no, what's happening to the lights? Scored less than 1,000. Cool. Pretty sweet. I like this. Great. Fantastico. So, I'm going to be using this notation for the rest of the video, this probability notation, but it really means the same thing as this proportion question. Man, I think we hit the witching hour. This rabbit is like going crazy. So anyways, let's go ahead and move on to a more interesting question. So just using that same method, figure out where the standard deviation was and do the math. Well, did we actually do the math? We never did. Well, we did 16%. And how I did that was I added up the empirical rule, 0.15% plus 2.35%, which is 2.5, and then plus 13.5%. So I'm adding up these three regions here. Boom, boom, boom. Okay, I think I'm repeating myself, so let's move on. Now here's a more interesting question. What proportion of 2020 SAT scores were less than 934? Now the reason this is a more interesting question, and this is where we should say, this is a problem because 934 does not fall on one of these boundaries from the empirical rule. It doesn't fall here, and it doesn't fall here. 934 is in between these boundaries. It's a little bit of an issue. So now I'm going to teach you how do we do this, answer the question not just for the ones that fall right on those empirical rule boundaries, but how do we answer this question if we want to use any number, right? What's the probability that a randomly selected student scored less than 934? Okay, let's do this. Here's the steps. I'm going to walk you through it. Okay, so same question. I'm just repeating here. Let me change my color. The first thing that you do, and if this was an AP exam question, by the way, you are going to have to answer a question like this. I can almost guarantee it. This is just so important. So the first thing you want to do is draw a curve. We may need to pause the video here because drawing a normal curve takes a little bit of practice. You can put arrows on the curve if you would like to indicate that that technically does go on forever in both directions. It gets asymptotically close to that horizontal axis. So first thing you do, you draw the curve. Next thing we do is we label the axis. So we'll come on through and I'll say, all right, so what was my mean? I come through, my mean was 1150. And then the expectation is that you come through with your curve and you label a couple standard deviations out in each direction where things were. So 1150 plus 150 is 1300, and then 1450 this way. Heading back is 1000. Heading back one more is 850. So draw the curve. This is expected. This is part of those scoring guidelines that we struggled with on the free response questions. It's looking for a labeled axis. It's looking for a curve. And the next thing it says is shade the area. Where's the area of interest? Where were the scores less than 934? So I can come over here. 934, well, this goes in steps. This is steps of 150. So if I go down 50, that would be 950. So it's going to be a little bit less than that. So now we say, all right, what's the area of interest on our curve? Remember that the total area under a density curve adds up to 1 or 100%. So this is where it gets a little bit difficult. How do we figure out where that is? Well, we can use the empirical rule to know that our answer is somewhere between this value falling on this value and falling on 850. Okay, it's somewhere between that 16% that I had mentioned earlier, somewhere between this 16% and just 2.5%. So it's between 2.5 and 16%. So somewhere in here. So how do we know what the real answer is? And we're going to be able to get this accurately using a couple different methods, okay? So when you take, you could use, if you're taking calculus-based statistics, this is where you would use calculus to answer the question, but it's actually, our calculators that we have in our classroom are perfectly suited to answer this question. All right, so let's jump in. I'm going to show you two ways to do it. The way to do it without the calculator and the way to do it with the calculator. And yes, you have to know how to do both. Okay, so we have our picture drawn. Now we're going to show our work. Now, way one to answer this question, so I'm going to come back here in just a minute. Way one to answer this question is, get out of here. Whoa, no. I want the cursor. There we go, thank you. Way one to answer this question, to find the area without a calculator, is you're going to use what's called Table A. Now, Table A is in the back of our textbooks. I think your textbooks might do it slightly differently. It reads maybe to the right or something like that. Not all tables read the same, but this is the one from the AP exam. I pulled this straight off the 2020 AP exam, which is I think the last formula sheet that was released. You're going to get this thing called Table A, and what it does is it looks at the area underneath the standard normal curve. So what we're allowed to do is we can take a look at the standard normal curve and we can see the areas held under certain standard deviations. So I'm going to teach you how to read this little table here. So for example, this number, let's go back to our, how do we know how much area is held to the left? So it's the shaded region to the left of one standard deviation below the mean. Well, one standard deviation below the mean is right here. We can see, I'll scroll up, where it says minus 1.0. One standard deviation below the mean, which is what we just did. I said it was 16%. And if you look here, it says 0.1587. So if you look at the top column, this is the tenths place, and then the row here is the tenths place, and the column is the hundredths place. So I go to negative 1.0. 1.00 is right here, and it gives us that 15%. So how many is held to the left of 2 standard deviations? Well, it's like 2.28 or 2.35. So close to what the empirical rule said. Okay. Now these numbers may be slightly hard to read. That's okay. We're going to use this table to answer this question. So what we're going to do is we're going to take that value of 934, which is where you want to label this on the exam, right? You want to draw this right here, 934. And you know what I might do? So this is not so laggy. I think I'm gonna maybe do this on a blank page, and then we'll come back to this picture to get our answer. And I know my answer is somewhere between 2.5 and 16%, or 2 points. Sorry, yeah, something like that. So let's take a look here. Insert blank page. Boom. All right, let's do this so it's not so laggy. So this is how we do this math. Let's keep that picture in our brain. It's really quite simple. So the first way to do it, this is the hard way, by hand. You say, well, let's start by calculating our z-score, right? I really want to know the probability. What's the probability that an observation falls below 934 SAT score? Well, what we can do is we can say, well, what's the z-score for 934? So we kind of go off on the side, and I'm going to skip this step. I'm going to do it all at once here eventually. So the z-score, we can call it z star, which is the z critical value of interest. We can say the z-score is equal to the value of interest minus the mean divided by that standard deviation. So let's go ahead and plug that in. That gives us 934 minus the mean of the distribution, which is 1150, divided by the standard deviation of 150. So now we just got to sit here and do some math, and we end up with a negative number on top, negative 216 divided by 150. Get out our calculators. Negative 216 divided by 150 is negative 1.44. So if x is our variable of interest, which would be the SAT score, saying what's the likelihood or what's the probability that a test taker scores less than 934 is the same thing as looking at the standard normal curve. And by the way, when I say standard normal, that means mean 0, standard deviation of 1. It's looking at our z-scores. It's the same thing as looking at that table and looking for, well, this 934, that was 1.44 standard deviations below the mean. Okay, so what we can do is we can say, well, what's the likelihood that z is less than z star, our z critical value, which is the probability that we go to our standard normal table is less than negative 1.4. Now I realize 1.44. I realize this is all new to you guys. It's going to look really weird. What's the likelihood that we would see something less than 1.44 standard deviation? So we just go to our table here. Let's jump to the next slide. And we're going to go, all right, I want to the area to the left of negative 1.44. So I find negative 1.4, and then I go over 1.401234, which is 0.0, that's the value, 0749. So I go back to my problem, is 0.0749. So what does this number mean? This is our answer. this is the answer to the original question. That original question being, what proportion of SAT scores were less than 934? The answer is 7.49% if you move that decimal place over. 7.49% of test takers scored less than 934, and we can use the information that we know and this idea of a z-score. This is really exciting. Okay, well, it turns out there's a much easier way to do it. So the calculator can do this instantly. We don't have to use a table. We don't have to calculate a z-score. So let's do it the easy way. You'll also notice that there's a second page to the table here. So the first one is only the values up to 0, which if it's 0.0 standard deviations below, you're going to have 50% of the data on the left, 50% of the data on the right. That's because it's symmetric, right? However, if you go to the next page, it's all the ones that are positive, and all of these it's slowly approaching 1. And if you go to 3.49 standard deviations out, you have 99.98% of the observations are less than 3.49 standard deviations. So pretty cool little table. All right, so it's only looking left. It's only looking at percentiles here. Okay, way number 2. Way number 2 to answer this question is just to use a calculator, and it's very simple. You get out your calculator. So we may need to take a break here, and if you guys don't finish the video, feel free to pause today. This is going to be kind of a long one, but that's okay. Grab your calculators. Make sure everyone's got a calculator. Maybe you guys passed it out. Maybe I was smart enough to put that in the sub notes, or not. Who knows? You're going to press second, and then vars, which is actually the thing that says distribution. So vars is below the circle right there. So second vars, and when you see that, you're going to see lots of options. You're going to press option 2, the one that says normal CDF. Now, what normal CDF does is you enter 4 things. It's for the normal curve. You enter the lower value of interest, so for the area. In this case, the lower value there is no lower value. The default value is some extremely large number in scientific notation. I typically use just something really big and negative if you're going on this side. Okay, so your lower value, I usually use like negative 1,000 or something like this. The upper value, if you're reading like off the table, the upper value is the value of interest. So if I were plugging this in to get my answer naturally here, I would use for the lower value negative 1,000. You could use negative 10,000, whatever, something super, super negative. The upper value here is 934. The mean, you know what? I did remember something about this trick. The mean, what was the mean for this? 1150, and the standard deviation is 150. Now, when you do this on the AP exam, when you use this normal CDF function, what it's going to give you is it's going to return and give you back the area under the curve between those boundaries. That is the orange and the red thing. On your test, this can be a method of showing your work. However, you must state what the numbers mean, and if you don't, you will be marked down. And so you can lose everything very quickly if you don't state that the lower boundary is negative 1,000, the upper boundary is 934. So if on your test you were to just write normal CDF, negative 1,000, 934, 1150, 150, you're going to get marked off. But if you say normal CDF, lower equals negative 1,000, or lower bound equals negative 1,000, upper bound equals 934, mean equals 1150, and standard deviation equals 150, and then you press enter and you write down the percentage that you see, you're going to see that we get about something very close to 0.0749, which is the same answer we got before. So you guys can try that right now and test it out and make sure it works. Similarly, you could have also used the standard normal values. You could have said negative 1,000 up to negative 1.44 with mean 0, standard deviation 1. You'll get the same answer, 0.0749, because it does all the math for you. This one's the easiest. The bottom one is the easiest one to plug in there. So give that a shot. Make sure you guys can get this value. And I'm just going to really quickly double check that that's what it is. Negative 1,000. And I think you have to use the negative button and not the minus button. The negative button is below 3. And then 1150 and 150. Yep, 0.0749. So 7.49% of the test takers scored below 934. Let's keep going. So now let's answer some tougher questions. We're going to follow along and answer these both ways, and we'll go for it. You guys can stop the video and see if you can answer this with the table if you'd like. It's a little bit tricky, but first you want to do is draw the picture. We're going to follow those steps. I may not use the color coding that I did before. I might just do everything in black. The stopping distance for a certain sedan model going 62 miles per hour is approximately normally distributed with a mean of 155 and standard deviation of 3 feet. What percent of braking incidents from this model would slide past 160 feet? So we're going to start by drawing our standard normal curve, or rather drawing our normal curve. So it's got the hump and then it comes down like this. Okay, like that. We need to label our axis. So 155 is right here. And then every standard deviation up that we go, like so, we're going to add 3. So that'll be 158, 161, and a number, 164. Yeah. Whatever, you probably don't even need that one. And then going down this way, subtracting 3, 152, man, I'm really tired, 149, so on and so forth. So draw a curve, label the axis. You can also say, hey, this is a normal distribution with mean 155. This is a quick way to write this, and you would put feet in both of these boxes. So mean 155 feet, standard deviation 3 feet. Okay, great. Now, the next step was to shade our area. What is our area of interest here? We're looking for 160. So these are in steps of 3. So 159, 160, 161. So we're looking really for what percent of accidents from this model would slide past 160 feet? Well, that is this area, about what percent? So we can shade the area, and you have to shade the area on the exam. But this is where it gets a little bit tricky, because in order for us to answer this question, we have to use this table. And this table only reads to the left. It doesn't read to the right. So we got to get a little tricky. We got to use some knowledge that we know. We know that the total area under the curve is 1. It's because it's a density curve for the standard normal distribution. So you can actually do this with normal CDF immediately, and you can just say, all right, normal CDF from 160 to some super ridiculously big number like 1,000 or 10,000, mean 155, standard deviation 3, done, and you get the answer immediately, and it should be 57.208%. So if you were doing normal CDF, and I'm actually going to write it, let's just do that one first so we can see what it would be. So if you were to actually write this on the exam, you would write normal CDF like this, and then in here you're going to write your lower equals 160. Oh my gosh, computer cannot handle this. I got to do it on a new page. Insert blank page. It doesn't matter where I write it. Oh, there we go. Normal CDF lower equals lower bound equals 160. We need to see that picture. It's just too hard without the picture. If it's slow on both ones, whatever. Upper equals, upper bound equals, I'm not going to write bound. Just pick a big number. 1,000 is usually what I do. And then mean equals 155. I'm trying to model good behavior for the test, and I know it's taking a long time. You might want to put this on 1.25 speed or something, or skip ahead. Standard deviation equals 3 feet. I don't know if you have to, I can't remember if you have to put units on there. Default to put in units if you need to. Lower 160, that's the 160 right here. Upper bound is this high value. And when you do this, you should get the answer when you're done, 0.5 7208 or something like that, 21 roughly rounded. So how do we do this the hard way? All right, if we want to do this the hard way, let's go back to inserting a blank page here. Let's try this again. To do this the hard way, we're going to say, I want to know for this distribution, when do I have, when are my observations greater than the value? Greater than 160. Greater than 160. So we're going to turn this into a z value now. So instead of saying when is my observation of my variable greater than 160, or what's the probability of that, we're instead going to ask what's the probability that we were to randomly select from the standard normal distribution, and we're going to use our z-score. We'll say, all right, well, I'm actually going to do 160 minus 155 divided by the standard deviation of 3. Or rather, let's not look at our distribution. Let's look at the standard normal distribution in the table. And yes, you have to know how to do this. So when is it greater than? So the question here is, when is the standard normal distribution greater than 160 minus 155 is 5 divided by 3, which is, what is the likelihood that a randomly selected item from the standard normal distribution is greater than 1.67, this is rounded, 1.67 standard deviations. So what you need to have in your head, this image, that 160, the z-score for 160 is 1.67. That's our z-score. So we need to go to the table, and we know, so we can kind of say, like, to figure out, and I'm just going to draw a little picture here, to figure out the area under the curve right here, what we can really do is, if we know the total area is 1, subtract this off, it's really equal to 1 minus the probability that the z-score is to the left of 1.67. Okay, and so what does 1 minus that probability look like? Well, that's going to give us this area. 1 minus, so that's this area, right? This thing right here is actually this area. And so if we do 1 minus that, we'll end up with the area that we want. And the reason we have to do that is because the table doesn't read to the right, it reads to the left. Okay. There is an argument you can make. You can say, Mr. Slagle, since this distribution is symmetric, can't I just look to the left of negative 1.67? Yeah, you can. Totally acceptable way to do the problem. So you can either do this 1 minus trick, or you can just look to the what would the negative version of this be? So you could also say, well, Mr. Slagle, this is equal to the probability that z is less than negative 1.67 because this distribution is symmetric. So we'll do it both ways. Either way should be pretty close. So I'll do this way first. 1 minus, go to the distribution, 1.67 standard deviations is 1.6. Let's fit this down. 1.60, 1, 2, 3, 4, 5, 6, 7, 9525. Yeah, 9525. All right, so let's go over 0.9525. So when I do the math there, we end up with something 0.4, sorry, 0. Erase that. 0.475. So basically, what does this mean in terms of the sedans? Well, in terms of the sedans slamming on their brakes, roughly 4.75% of the braking incidents from this model going 62 miles an hour would skid past 160 feet. So if you were investigating a car crash or something and you were like, oh, yeah, they claimed that they were going 62 miles an hour, and you went and measured the skid marks, and the skid marks were 170 feet or whatever, you'd be like, I don't think so, right? I don't think so, because that's very unlikely based on this distribution. There's only for 160, there's only a 4% chance. So if it went 170 feet, it's much less than that. So on. So there's your reasoning. So let's try this. What if we look to the left of negative 1.67? Let's go back to our table. Left of negative 1.67, we better get that 4. Negative 1.0, we better get that 4%. Negative 1.0, 1, 2, 3, 4, 5, 6, 7, 0.475. Yep, same number. Cool. All right, cool. Let's move on. All right. That was what I gave up there. Okay. All right, let's do some heavy metal distributions. I'm going to do this one the hard way and the easy way as well. The easy way, very simple. My favorite heavy metal band has songs with lengths that are normally distributed with a mean of 16 minutes and a standard deviation of 2.3 minutes. So this band, what proportion of their songs are between 13 and 17 minutes long? Well, we can do normal CDF here, and we just say normal CDF, our lower bound. Let's draw our picture. Let me be a good teacher. Sorry, let me be an okay teacher and draw our curve for the normal distribution here. All right, I got to put in a request for a faster computer. This thing is just brutal. Centered on 16, our distribution. Let's go up a couple standard deviations, 1, 2, like so. Plus 2.3 minutes would have it looking like 18.3 and 20.6. And when I go down, I subtract 2.3, 13.7, and 11. Brain 4. Thank you. All right. So I want to know, where's my area of interest? I want to know for this curve between 13 and 17 minutes. Well, this is 13.7, so 13 is like right here or something. I'm just guessing. And 17 minutes is like maybe right there. So this is the area under the curve that I'm interested in. Now, if you're talking about, and yes, you do need to shade it. This is really easy to do with normal CDF. So you can say to find this area, we can use normal CDF with our lower bound at our lower bound at 13, our upper bound at, as long as you label them, you're in good shape. Our upper bound at 17, our mean at 16, and our standard deviation at 2.3, and it'll give you that proportion of songs. Okay, if you want to do this by hand and show your work, this is how you would do that. Hopefully this works. So we'll do, what's the probability that an observation randomly selected is greater than 13 but less than 17? I'm using kind of a old inequality notation as a compound inequality. Greater than 13 and less than 17. So we're going to do this all at once. Is we're going to find two z-scores here. My two z-scores are, well, the value 13 minus the mean of 16 divided by 2.3. When is that less than? So we're using our standard normal. This is the standard normal calculation, so we have to now put z in the middle because that indicates that standard normal curve. 17 minus 16 divided by 2.3. So I've switched to the standard normal distribution, and we're going to get two values there. What's the probability that the z is between 1.0 or 1.30 and, now we have to do a little bit of rounding here, so it kind of is a little brutal. So you would have to do this math: 13 minus 16 divided by 2.3, 17 minus 16 divided by 2.3. Okay, and since this is going to be negative, a little bit, it'll be negative 3 divided by 2.3, so you should get something a little bit bigger than 1 or more extreme than 1. And then this will be 1 divided by 2.3, so we're getting this value 0.4348. So rounded would be 435. That's okay. So we're looking at the standard normal curve here. And so how do we calculate this? Well, there's a couple ways that we can think about it. You can take one, and then you can, the easy way is to just plug it into normal CDF with this is your lower bound and this is your upper bound. You can take one and subtract off this or subtract off that. But the easy way to think about this is actually equal to, imagine if I just, because our table reads to the left, so I'm going to take everything to the left of this number, and then I'm going to cut away or subtract off everything to the left of this number. So that would be, this is equal to the probability that z is less than 0.435, which was the z-score for 17, right here, 0.435, minus the probability that z is less than the z-score for 13, which is negative 1.3. Okay, so I want you to have this picture in your head. So really what we're doing here is we have two curves. Okay, the curve on the left is this one that's past this hump. Oh my gosh, my computer. We have all this area over here, and then this one is this, and we're subtracting off that chunk to get our area of interest. All right. So now what we would do is, since we have two areas that are left reading, I can go to my table and I can find 0.435, 0.435 is halfway between these two. So you can say, oh, 6664 and 6700. What's the halfway point between those two? Or you can just pick whichever one is closer and it'll just be an approximation. That's fine. 0.6700 minus 0.6664. 0.36 divided by 2. So add 18 to plus 0.6664. 0.6682. So the reason I went halfway between these is because the value said 0.435, or you could just pick 0.43 and round down. That's perfectly acceptable. Let's just do that. The 0.6664, we're rounding, or no, we would round up. So we do 0.670. We'd round up because of the calculation. Well, it doesn't matter. Let's just keep it 0.667. We'll call it good. All right, so I'm going to go back to my problem. Oops. So that was 0.667. Euler's kicking on. And we're going to subtract off the area to the left of negative 1.3. I really don't feel like going back to the table. I wrote that down, and I think the one that I got here is 0.0. You guys can practice 968 for that area. And when we subtract those, we should get a very close or a similar value to what you did with normal CDF. Now, mine was a little bit different. It was off by like a little bit of a percent. So you'll get 0.56. I don't know. I used a different number in my notes. Let me just do the math really quick. 0.667 minus 0.0968. Which is 0.5702. Let me erase that. The computer, 5702. Okay, great. And it's off a little bit from the normal CDF. Normal CDF is going to be very accurate. This is a little bit rounded. That just has to do with the fact that we had to do some rounding and truncation of the numbers when we were putting them into the table, but that's how you do it. So what does this number mean? How do we interpret the number? This means that roughly, or about, 57% of Mr. Slagle's favorite band's heavy metal songs are between 13 and 17 minutes long. About 57% of this band's songs are between 13 and 17 minutes long. Pretty sweet. All right, last couple here. The last couple. Mr. Slagle's favorite heavy metal band, blah, blah, blah. The question asks, what the longest 12% of song lengths that this band writes are at least how long? Now, this is a different question. This is a different question entirely. This is saying, all right, this is a question about the band. If we were to take all their songs and we were to sort their lengths from least to greatest, the longest 12%, if this area was 12%, and I'm just making up the drawing here, that would mean that this side has 88%. What we want to know is what is the song length? What's the song length that splits the curve? That's what this is asking. The longest 12% of song lengths are at least how long? How long are those songs? So, it's a different question. What we want to do here is slightly different. We're going to need to use that z-score formula. The z-score is equal to the value minus the mean divided by the standard deviation, and we know that. So the real question is, if I'm looking at this distribution, let's look at our table and let's find 88% in our table. This is way two. So you draw the distribution, right? You label the distribution and you shade the area. We're really looking for this area here for this question. Now what we're going to do is we're going to go to the table and we're going to find where 88% is to the left, because that's the same boundary as where 12% is to the right. So let's go back to here. 88% to the left. Looks to me like, zoom in, I want to try and get as close to 88% as possible. So we're actually not looking at the z-scores here. We're looking at the probability under the curve, 88%. So 87, 87, 87, 87, 9, 88, 10. Oh, look at this. They're both equally as close to 88%. So we would say that this is, following the number back, 1.17 and then halfway between roughly 1.175 standard deviations. So what we can say here is the z value for this is equal to 1.175 roughly for the standard normal curve. So if we're looking at the standard normal curve, 88% of the observations are held less than 1.175 standard deviations. So I'm going to come over here. We don't know what the value for our distribution is, but I know what the mean is, and the mean is 16, and I know what the standard deviation is, it's 2.3. So now we can solve this equation by doing some clever algebra, multiplying both sides by 2.3, we're going to get 2.7025 equals the value minus 16, and then add 16 to both sides. So the value of interest, or rather the x value of interest that we want, is that value, or x, equals 18.7025. What does this number mean? This means about 12% of this band's songs are 18.7025 minutes long, or longer. About 12% of this band's songs are 18.7025 minutes long or longer. That's the boundary between for the longest 12% of the songs. Now you can also do this on your calculator. So instead of using normal CDF to find the area, instead you just say inverse normal, and then for the area here, you just plug in the area of interest, which would have been that 88%. Now we don't get the exact same value, but it's pretty close. 18.714 is what it gets. So it returns the percentile for the area that is entered. Now, if you plug in mean 0, standard deviation 1, it's going to give you back this value, 1.175. But if you plug in mean 16, standard deviation 2.3, it's going to spit back the actual answer that you need, which is that 18.702 or whatever, or 18.714 if you're doing normal CDF. And they're not exactly the same because the tables we have to round. Okay, for your homework, always use way 1 and then check your answer with a calculator. If you have not downloaded the TI-84 app from the App Store, you need to do that ASAP so that you can practice how to use this for the exam. That's the end for the video. Hope you enjoyed it. This one was a monster. Yeah, it's immortalized on YouTube, so you can watch it over again. We'll see you next time.